This information is presented by Bluewater Auto Restoration. Welcome back. This is week 10 of the 2026 Bluewater Auto Restoration podcast.
It is great to be back here. 10 weeks already. It's moving fast.
It really is. It feels like we just started the year. But we release new podcasts every Saturday morning, so grab your coffee or maybe grab a wrench if you are listening out in the garage.
Always a good place to listen.
Definitely. Today, we are doing a deep dive into something that, honestly, I think starts more arguments at car shows than almost anything else. We are looking at blueprinting an engine. Is it worth it?
Oh, yeah. That is a heavy, heavy word in this community.
It really is. It sounds expensive. But before we get into the weeds, I do want to remind you to visit the BlueWaterAutoRestoration.com website.
Lots of great visuals and resources over there to go along with our deep dives.
Exactly. And a quick reminder, our podcasts are available on Spotify, YouTube, Apple Podcasts, or SoundCloud. So however you prefer to listen, we are there.
So blueprinting. Where do we even start with this one?
Let's start with a scenario. Paint a picture for you. You're at a local car show. It's a nice Saturday evening, sun is going down. You are walking past a row of really beautiful muscle cars.
I can picture it.
Right. So you see a gorgeous 68 Chevelle. The paint is perfect, the hood is popped, and the owner is standing right there in his folding chair holding court.
Let me guess, he's got his arms crossed.
Oh, absolutely. Arms crossed, looking proud. You ask him about the motor, and he points to this chrome-covered big block and says, yeah, she's fully blueprinted.
There it is. The magic word.
The magic word. And the implication there is instant, right? He is telling you, without saying it, that his Chevelle is inherently superior to the identical Chevelle parked 2 spots down.
Because it's not just rebuilt. It is perfected. That's the vibe he's going for.
Exactly. It's the ultimate status symbol for gearheads. But here's the major conflict we found when digging into the research for this deep dive. Is that engine actually blueprinted? Or did he just buy into a mountain of sales hype?
I would bet heavily on the sales hype. Look, it's the most abused word in hot rodding today. 4 out of 5 people who claim their engine is blueprinted probably haven't actually had the full process done.
That is a staggering number. So they are just lying?
Not necessarily lying on purpose. They might genuinely believe it. They might have bought a box that said blueprinted high-volume oil pump or a blueprinted camshaft,
Right.
and they bolt that part on, and suddenly, in their mind, the whole engine absorbs that magic. But the reality of a true blueprint is a totally different universe.
It reminds me so much of the word billet. You know, you open a parts catalog and everything is billet shift knobs, billet valve covers, billet control arms.
Oh, billet is the perfect comparison. People see that word and they instantly think, aerospace technology, super strong, unbreakable.
It's like it's made of vibranium or something.
Right. But if you actually talk to a metallurgist or just look in the dictionary, a billet is literally just a bar of steel or a block of aluminum. It just describes the raw, uncut shape the metal came in before it was machined.
It doesn't mean it's better metal.
Not at all. You could have a billet of pure lead. It would be entirely useless for making the control arm. It would just bend. But hey, it's billet.
So marketing departments just took that word and turned it into a synonym for premium.
Exactly. And blueprinting has suffered the exact same fate. It's become a buzzword to justify adding $2,000 to a price tag.
Which is exactly why we are doing this deep dive. Our mission today is to completely separate the marketing fluff from the mechanical reality. We want to show you what true blueprinting entails and help you decide if it is actually worth your hard-earned cash.
And it is a lot of cash, so it's an important question.
Let's jump into section 1, defining the undefinable. What actually is blueprinting?
Well, Webster's dictionary says it's just a detailed outline or plan of action.
Which is entirely useless for us. I have a plan of action for mowing my lawn, but I'm not blueprinting my yard.
I mean, you could try. But no, in engineering terms, it's much more rigid. Blueprinting is the active pursuit of a mechanically optimized assembly.
Mechanically optimized.
Yes. You are trying to minimize every possible energy loss. Friction, heat, vibration, you want all of that gone so you can maximize output. It's precision restoration at a microscopic level.
Now, I have to clear something up because the research brought this up and it made me laugh. When I was a kid, I honestly thought blueprinting meant you wrap the engine block in blue paper.
You were not the only one who thought that.
It just sounds so literal. But there is no blue paper involved.
No blue rolls of paper. The term comes from the concept of returning the physical engine back to its absolute perfect original design specifications, the blueprints.
The theoretical ideal.
Exactly. It starts on paper, sure. You calculate your compression ratio, your displacement, your deck height. But the actual work is about physical verification, making the metal match the math.
Which brings up a really crucial distinction. Factory specs versus blueprint specs. I think a lot of people, they assume if an engine rolls off the assembly line at Ford or GM, it is perfect.
That is a very common misconception. A mass-produced engine is far from perfect. It is just good enough.
Explain that. Why wouldn't it be perfect?
You have to think about the factory environment. They are pumping out thousands of engines a shift. Speed is everything. They cannot afford to stop the line and measure every single bearing with a micrometer.
So they use ranges.
Exactly. They rely on tolerances. Let's take a main bearing clearance as an example. That's the tiny gap between the crankshaft and the engine block.
Where the oil lives.
Right. The factory spec sheet might say the acceptable range for that gap is anywhere from 0.0015 inches to 0.0030 inches.
Which, to the naked eye, is basically nothing. We are talking thousandths of an inch.
To us, it's nothing. Inside a running engine, it is massive. Because of hydrodynamics, the metal of the crankshaft shouldn't actually touch the metal of the bearing. It rides on a pressurized wedge of oil.
Like a hydroplaning tire.
Perfect analogy. Now, the thickness and the stiffness of that oil wedge depend entirely on the size of that gap.
Okay, so if the factory says anything from 15 to 30 10,000ths is fine.
Then you might get an engine where the first main bearing is really tight, right at the minimum, and the bearing right next to it is really loose, right at the maximum.
The factory says ship it, it's in spec.
They stamp it approved.
Yeah.
But oil is lazy. Fluid dynamics dictates it will take the path of least resistance.
So the oil gushes out of the loose bearing.
And it starves the tight bearing.
Wow.
So now you have uneven oil pressure across the block. You have uneven heat generation. You have one bearing working way harder than the rest. It will run, sure, for 50,000 miles, maybe 100,000, but it's not optimized.
Enter the blueprinter.
Exactly. A blueprinted engine removes the word range from the vocabulary.
So there is no between.
None. The builder looks at the application. Is this a drag car, a street cruiser, a boat? And they pick an exact target number. Let's say 0.00275 inches.
And it has to be exactly that.
It either is or it isn't. Every single main bearing gets machined or matched to be exactly 0.00275. Consistency is the entire game.
And that leads into this concept of stack-up error, which I found fascinating in the research. Stack-up error?
Oh, stack-up error is the silent killer of factory horsepower.
It sounds like a software glitch.
It's a geometry glitch.
Mm-hmm.
Think about all the parts that stack on top of each other. You have the engine block deck, that flat surface on top. Due to factory machining speed, maybe that deck is tilted left by 0.02 of an inch.
Okay, slightly crooked, but within the factory tolerance.
Right. Now you put a head gasket on it. Maybe the gasket manufacturer had a slight variance and it's 1,000 thicker on the right side.
Still on spec.
Still in spec. Now you bolt the cylinder head on top. Maybe the casting shifted slightly in the sand mold, so the combustion chambers aren't perfectly uniform.
So individually, every part passed quality control.
Yes. But when you stack them all up, the errors compound. You might end up with cylinder number 1 having a significantly larger combustion space than cylinder number 8.
Meaning cylinder 8 is squeezing the air and fuel much tighter. It has higher compression.
Exactly. And higher compression means higher heat. So cylinder 8 is running hot. It might start to detonate or knock.
And you can't just tune the carburetor or fuel injection for one cylinder.
You can't. You have to tune the whole engine to keep cylinder 8 from blowing up, which means you have to retard the timing or add extra fuel.
Which kills the power in the other 7 perfectly fine cylinders.
That is the tragedy of stack-up error. You leave horsepower on the table to protect the weakest link. Blueprinting fixes this. You machine the block perfectly square, you measure the gaskets, you grind the combustion chambers so they all hold the exact same volume of liquid.
You essentially make 8 identical single-cylinder engines that just happen to share a crankshaft.
That is the best way to describe it.
Okay, so that is the theory. Let's get into section 2, the true blueprint. Because when we say exact, I don't think people fully grasp the sheer insanity of what that takes.
Insanity is the correct word. This is the extreme end of the spectrum. This is professional race shop territory.
Checkbook engineering, right?
Total checkbook engineering. You need an unbelievable amount of time, and an unbelievable amount of parts.
Wait, parts? Why do you need extra parts? If I buy a set of forged pistons, I have a set of pistons.
If you are building a normal street motor, yes, you open the box, you wipe them off, you put them in. But if you are chasing a true blueprint, the research highlighted a high-end drag racing builder who had to order 3 complete sets of premium pistons for one V8 engine,
3 sets, that's 24 pistons.
just to find 8 that matched perfectly.
That is crazy. Are modern parts really that inconsistent?
They are incredibly consistent by normal standards. But pistons are forged or cast metal. When they cool, they shrink. Sometimes they shrink slightly at a round. We're talking variations of 10,000ths of an inch, or a fraction of a gram in weight.
But in this tier of engine building, the manufacturer isn't to blame. The standard is just that impossibly high.
Exactly. To build an engine with effectively 0 tolerances, you just have to buy volume. You measure all 24, pick the best 8, and the rest get put on a shelf for a different project. They did the same thing with connecting rods. Bought 4 sets just to get 8 identical rods.
The logistics alone are a nightmare.
And we haven't even talked about the valves.
Let's talk about the valves. The research had this amazing example from Steve Schlingmann at Southwest Racing Engines. They detailed the inspection process for a single intake valve.
This blows people's minds. Most guys building a motor at home, they grab a valve, look at the face, maybe roll it on the workbench to see if the stem is bent.
Right? Looks round, not burnt, good to go.
Schlingmann's shop runs a 15-point inspection on every single valve before it gets anywhere near a cylinder head.
15 points. Run us through some of these because it highlights how deep this goes.
Well, first is material. They actually use an alloy analyzer to verify the metal composition. You can't just trust the sticker on the box when an engine is spinning 9,000 RPM.
Trust but verify.
Then they check head diameter. But they don't just measure it once. They chuck the valve up, spin it, and measure it at 4 different locations
Why spin it?
to find out if it's oval-shaped. If it's not a perfect circle, it will not seal against the valve seat. You lose compression.
Okay, so material, head diameter, what's next?
Stem diameter. And they measure this longitudinally, meaning up and down the length of the stem, and angularly spinning it again.
Looking for a taper, like if the stem is thicker at the top than the bottom.
Exactly. Because if it's tapered, it will bind in the valve guide. Then they check the face angle, the margin width, the seat width.
We're still on one valve.
Still on valves number 1. Here's a really critical check. Valve lock location.
What is that?
You know, the tiny little grooves machined into the very top of the valve stem, the ones the keeper locks snap into.
Yeah, that holds the spring retainer in place.
Right. If the machine tool at the factory cut those grooves even 10,000ths of an inch too high or too low, it changes your installed spring height.
Oh, wow. I never even considered that.
It's massive. If the groove is too low, the spring is compressed tighter than the rest. Suddenly, one valve has 150 pounds of seat pressure, and the next one has 140. Your valve train is completely unbalanced.
At high RPM, that's valve float waiting to happen.
Exactly. So they measure the lock location. They check concentricity. Is the head perfectly aligned with the stem? They weigh it on a digital scale. They even use a precision straight edge to verify if the face of the valve is perfectly flat or dished.
So they do all of that. 15 measurements, and then they pick up valve number 2.
And do it 15 more times.
Yeah.
And then 16 exhaust valves. And then the springs, the push rods, the lifters.
It sounds absolutely exhausting.
It is entirely exhausting. And that answers the question of why true blueprinting costs $10,000 to $20,000.
It's the labor.
It's almost all labor. You are paying a master machinist $150 an hour to measure valve stems for 2 solid days, plus the cost of the wasted parts.
So it's safe to say the guy in the folding chair at the car show did not do this.
Highly unlikely.
But maybe he did a backyard blueprint, which brings us to section 3. Because for the mere mortal enthusiast, dropping 20 grand on machine work is just not happening.
Not if you want to stay married, usually.
Right. So the big question is, can the average person in a 2-car garage achieve, say, 90% of these results for a fraction of the cost?
The research says absolutely yes. But it requires a complete shift in how you think about measuring things.
The feel factor.
The feel factor. Your hands and your fingers are incredibly sensitive instruments if you train them.
This was the most surprising part of the deep dive for me. I always assumed the guy with the most expensive digital micrometer wins. You see guys on forums flexing their $500 Mitutoyo mics.
High-end micrometers are beautiful tools, but for a novice, they are a massive trap.
How so?
A micrometer measures by squeezing a part between an anvil and a spindle. They have a little ratchet stop on the end so you don't squeeze too hard.
What?
But if you just turn that thimble a tiny bit too aggressively, you actually flex the C-frame of the micrometer itself.
You bend the tool.
Just by a 10,000th of an inch, but that ruins the measurement. Or, if you hold the frame in your warm hands for too long, the metal expands from your body heat, and your numbers change.
So you could hand the exact same piston and micrometer to 3 different guys in a garage and get 3 different numbers.
You absolutely will. So the alternative for the backyard builder is to rely on simpler tools combined with physical sensation. Dial calipers are great for general sizing because they are much harder to mess up. But the real secret is plug gauges.
Explain a plug gauge to me. Let's
Yeah.
pretend I'm standing at my workbench right now.
Okay, a plug gauge, sometimes called a pin gauge, is just a precisely machined cylinder of hardened steel. It looks like a little metal dowel pin. You can buy a whole set of them in varying sizes for about $100.
Okay, so I have a box of perfectly sized metal pins. How does that help me blueprint?
You use them to calibrate your hands. Let's say you are checking the lifter bores in your engine block. You want to make sure they aren't worn out. You take a plug gauge that matches the factory spec perfectly. You slide it into the bore.
And I just feel it.
You feel the drag. You slide it up and down. Is it sticky? Does it glide like glass? Can you wiggle it side to side? You memorize that physical sensation.
That sensation is what perfect feels like.
Exactly. Then you take your actual hydraulic lifter and you slide it in. Does it feel identical to the plug gauge?
If the plug gauge took a firm push, but my lifter just falls right through to the camshaft.
Then you know immediately your lifter's undersized or the bore is tapered. You aren't trusting a digital readout that you might have botched. You are comparing physical reality.
That is brilliant. It's like training wheels for your hands.
It removes so much user error. And for the most critical part of the bottom end, the bearing clearances we talked about earlier, the backyard builder's best friend is plastic gauge.
Oh, the little green strings of wax. I remember using that on my first engine rebuild.
It seems so primitive compared to laser measuring tools. It's basically a piece of waxed thread inside a paper wrapper.
For those who haven't used it, you cut a piece of this wax string, lay it across the crankshaft journal, and then bolt the bearing cap down over it.
You torque the bolts to their final spec, then you take it all apart. The wax gets squished flat between the bearing and the crank.
And the wrapper it comes in has a little printed scale on it.
Right, you hold the paper scale up to the squished wax. The wider the squish, the tighter your clearance is.
Is that really accurate enough to call it blueprinting, though?
It absolutely is for a street engine.
Yeah.
Because plastic gauge measures the actual real-world clearance in the fully assembled state. It automatically accounts for any weird distortion in the bearing cap when the bolts stretch.
It measures reality, not theory.
Exactly. If you use plug gauges, dial calipers, and plastic gauge, and you take the time to check every single ring gap, every bearing, every bore, you can easily hold tolerances within plus or minus 1/1000th of an inch.
Which is fantastic.
It won't get you a job building Formula One engines, but for a muscle car or a daily driver, it will rival a $1,000 machine shop job.
Using your brain more than your bank account. I love that strategy. So that covers the dimensional side of things. But we need to move into section 4 because there is another word that always gets stapled to blueprinting.
Balanced and blueprinted.
Balanced and blueprinted. People say it so fast it sounds like one word. Balanced and blueprinted. We need to clear up the confusion between the two.
They do go hand in hand like a suit and tie. You can wear the suit without the tie, but it looks a bit unfinished.
Yeah.
But they are completely distinct processes. Blueprinting is strictly about dimensions, making sure sizes are correct. Balancing is about mass, making sure things spin without shaking themselves apart.
So if I am doing my backyard blueprint on a budget, is balancing optional or mandatory? Do I have to pay a shop to do this?
The answer is it depends on what parts you are using. If you are doing a high-quality rebuild using the original factory parts, the stock crank, stock rods, stock pistons balancing is highly recommended but technically optional.
Because the factory already balanced it.
Right. They balanced it well enough for the factory red line. But, and this is a massive, but if you are upgrading to aftermarket components, balancing is absolutely mandatory, non-negotiable.
So if I buy a stroker crank or some forged H-beam rods or lightweight pistons, I have to balance it. Why? What if I buy them from the same company?
Even then, the physics of it comes down to the counterweights on the crankshaft. Have you ever looked at a bare crankshaft?
Yeah, it has those big, heavy lobes of metal hanging off the opposite side of the rod journals.
Those are the counterweights. Their entire purpose in life is to offset the specific mass of the piston and rod that are moving up and down.
Okay.
So if the engineers at Chevrolet designed those counterweights to offset a heavy, thick, cast aluminum piston,
And I swap in a super light, modern, forged racing piston.
then your counterweight is suddenly way too heavy for the piston. It's offsetting. The scale is tipped.
What happens when you run it like that?
Violent vibration. And I don't mean a little rattle in the dashboard. I mean harmonic dissonance. It's like taking a sledgehammer and violently hitting your main bearings 6,000 times a minute.
That sounds catastrophic.
It is. It will destroy the oil film. It will crack the main caps. It can literally snap the snout right off the front of the crankshaft.
All right, consider me terrified. Balancing is mandatory. Walk us through the step-by-step process. What happens when I drop my parts off at the machine shop?
Step 1 is weight matching. This is focused purely on the reciprocating parts, the pistons and the connecting rods. The machinist takes a highly sensitive scale, accurate to 1/10 of a gram, and weighs all 8 pistons.
Okay, looking for the lightest one.
Yes, you find the lightest piston in the set. That becomes your target weight.
Because it's a lot easier to take metal away from a heavy piston than it is to glue metal onto a light one.
Exactly. You cannot safely add weight to a piston. So you take the 7 heavier pistons, flip them upside down, and carefully grind or drill tiny amounts of aluminum off the underside, usually around the pin boss area where it's thickest,
Until all 8 weigh exactly the same as the lightest one.
down to 1/4 of a gram. Then you move to the connecting rods. But rods are a lot trickier.
Why? A rod is just a chunk of steel.
But it's a chunk of steel that moves in 2 different dimensions simultaneously. This is step 2, the fulcrum. The big end of the rod, the part that bolts to the crank, is rotating mass. It spins in a circle. The small end, the part attached to the piston, is reciprocating mass. It only moves straight up and down.
Wow, I never thought of it isolating like that.
You have to measure them isolated. The shop uses a special jig. It supports the small end on a frictionless bearing while the big end rests on the scale.
So you weigh the big ends of all 8 rods.
Match them all to the lightest big end, then flip them around, weigh the small ends, and match them all to the lightest small end.
That sounds incredibly tedious.
It takes hours.
Hmm.
But if you skip it, your engine will vibrate. So now your pistons are perfectly matched, your rods are matched. Now we move to step 3, dynamic balancing.
This is where the crankshaft gets involved.
Yes, the machinist calculates what's called the bob weight. It's a mathematical formula that totals up the weight of 1 piston, 1 rod, the rings, the wrist pin, the locks, and even an estimated weight of the oil clinging to the parts,
They factor in the oil.
down to the gram.
Mm-hmm.
They take that total bob weight and they bolt physical metal weights onto the rod journals of the crankshaft to simulate the parts being attached.
And then they spin it.
They drop it into a dynamic balancing machine. It looks exactly like the tire balancing machine at your local tire shop, just heavier duty. They spin the crank up to speed, and the sensors in the machine measure the wobble.
It finds the heavy spot.
Exactly. The computer screen tells the machinist, you need to remove 20 grams of weight at this specific angle on this counterweight.
So they get out the drill.
They get a massive drill bit and bore holes into the counterweights to lighten them up.
That explains why I always see racing cranks that look like Swiss cheese.
Exactly. But what if the scenario is reversed? What if you were building a blown, nitrous-injected monster and you bought massive, heavy-duty pistons? Now your parts are heavier than the counterweights.
You can't drill holes to add weight. What do? Weld extra steel on.
Welding changes the heat treat of the crank. It weakens it. So they use something called Mallory metal.
Mallory metal. I love this part of the research. It sounds like something straight out of a comic book, like vibranium or adamantium.
It's a real thing, and it's fascinating. Mallory metal is a tungsten alloy. The key property of tungsten is that it is incredibly dense. It's roughly twice as heavy as standard steel.
So it packs a lot of mass into a tiny space.
Right, so the machinist drills a hole parallel to the crank journal, right into the counterweight. Then they take a small slug of this Mallory metal, maybe the size of a roll of pennies, and press fit it into the hole, then weld the very edges to trap it.
So you instantly add a massive amount of weight without changing the external shape of the crankshaft.
Exactly. It's like adding lead tape to a golf club, but permanently embedded inside the steel.
That is just so cool. So after all this drilling and plugging, the crank spins perfectly smooth. And the benefit is what? Just a smoother idle.
Smoother idle, much faster revving, because the engine isn't fighting its own internal imbalances. But the main benefit is longevity. That harmonic sledgehammer we talked about is gone. The oil film stays intact, the main bearings survive, the engine lives a long, happy life.
Which brings us to the ultimate question, Section 5. The ROI, return on investment, is it worth it? We need to give our listeners a verdict.
The research provided a great framework for this, the blueprinting choice matrix.
Let's break down the variables. It depends on engine type, intended use, RPM range, and budget.
Let's look at the actual data first. What are the tangible benefits? If someone drops $5,000 on professional blueprinting and balancing, do they get a massive horsepower spike? Like 50 extra horsepower?
Brace yourself for this one.
Yeah, the truth hurts. No. Typically, a fully blueprinted engine only yields a 2 to 5% power gain over a standard non-blueprinted rebuild.
2 to 5%. So on a mild 300 horsepower street engine, you are gaining, what, 6 to 15 horsepower?
About that. You literally cannot feel 15 horsepower in the seat of the pants in a heavy steel car.
So if it's not for power, what is the ROI?
Efficiency and reliability. Because every cylinder is perfectly uniformed, your piston rings seal perfectly, you have less blow-by, you have less parasitic drag from friction. The engine runs cooler, it runs cleaner, and the parts wear evenly.
So it's an investment in the future, not a dyno sheet today. Let's run through some concrete scenarios for the listeners. I'll pitch the build, you give the verdict.
Sounds good.
Scenario A, the daily driver or Sunday cruiser. I am rebuilding a standard 350 Chevy small block for my pickup truck, or maybe a nice convertible. I drive it to get ice cream. It rarely sees 4,000 RPM.
The verdict is absolutely not worth the full professional cost.
Not worth it.
No.
Yeah.
The factory tolerances are perfectly adequate for driving to the grocery store. Spending thousands of dollars to meticulously document every clearance is a massive waste of your budget.
Do the backyard check, but don't pay the big bucks.
Right. Get a high-quality, conventional rebuild.
Yep.
Maybe do a standard balance job just to be safe, and take all that leftover money and buy better cylinder heads or an electronic fuel injection system. You will actually feel that difference.
Perfect. Scenario B, performance, racing, or high RPM street car. I'm building a track car or a canyon carver, and I plan on bouncing it off a 7,500 RPM rev limiter regularly.
The verdict, absolutely, 100% worth it. Mandatory.
No hesitation.
None. Two major reasons. Number one, high RPM is the enemy of imbalance. A minor vibration at 2,000 RPM becomes catastrophic at 7,000 RPM. The forces increase exponentially.
So it's about keeping the parts inside the block.
Exactly. And reason number two is repeatability. If you are racing and you blow an engine mid-season, you have to drop your backup engine in. If your backup engine isn't blueprinted exactly like the primary, it will have a different power curve.
And that messes up your gearing, your suspension tuning, everything.
You'd have to relearn the car. Blueprinting guarantees engine A performs exactly like engine B.
Makes total sense. All right, final one. Scenario C, historical or restoration. I have a 1967 Corvette. It's a 427 tri-power. Numbers matching. I'm never taking it to a track. I just polish it.
Verdict. Worth it. But for an entirely different reason than the race car.
Value preservation.
Bingo. That original numbers-matching engine block is literally irreplaceable. If a poorly clearanced rod bearing spins and a connecting rod snaps and punches a hole in the side of that block, you just lost 50% of the total value of the car.
Because it's no longer numbers matching.
Exactly. So in that case, spending $5,000 on blueprinting is the cheapest insurance policy you can buy to guarantee that original engine never destroys itself.
That is a great perspective. But the research did have a strong warning about the law of diminishing returns.
Oh, absolutely. There is a very real danger of falling into what builders call the chasing ghosts phase.
Where you are just spending money to satisfy your own OCD.
Exactly.
Yeah.
If you are building a mild street motor and you spend days agonizing over whether a bearing clearance is 0.0025 or 0.0026, you have lost the plot.
You're not building a satellite for NASA. It's a Chevy.
Right. No one close enough is actually good enough for your specific goals.
This has been such an incredible look under the valve covers. Honestly, I feel like I need to go out to my garage right now and apologize to my engine for treating it so poorly.
We all have those moments.
Let's wrap this up with a summary of the key takeaways for the listeners.
Good idea. Number one, blueprinting is about precision and executing a strict plan of action. It's about hitting exact target numbers, not just falling within a broad factory range.
Number two, there is a massive gulf between marketing blueprinting, which is just a word stamped on a box to charge you more, and true blueprinting, which is an obsessive, expensive process of weeding out parts to find perfection.
Number three, balancing. It is non-negotiable if you are using any aftermarket internal components. The physics demand it. Do not skip it unless you like the sound of breaking metal.
And number four, The backyard approach is completely viable. You don't need a $1 million CNC shop to build a great engine. If you have some plug gauges, some plastic gauge, and the patience to rely on physical feel, you can build a remarkably precise engine at home.
So true.
Now, before we sign off, I want to leave you with a final thought to chew on, something that wasn't heavily covered in the historical sources, but is incredibly relevant today.
Oh, the CNC evolution.
Yes, we spent this whole hour talking about how hard it is to achieve perfection, the measuring, the hand fitting, the grinding, but we live in 2026.
We do, and modern manufacturing has completely changed the landscape.
Right. Modern CNC machines can hold tolerances right off the assembly line that human hands 50 years ago could only dream of achieving. A completely stock, factory crate engine today is arguably blueprinted by 1960s standards just by virtue of the robots building it.
Which raises a really provocative question about the future of this whole industry. If the factory parts are becoming mathematically perfect right out of the box, will the art of blueprinting eventually die out?
It's a wild thought. Will the job of the master engine builder become obsolete?
From a purely mechanical standpoint, maybe? But I have to wonder if the human desire for better than perfect will always keep the art alive.
Even if the computer says it's flawless, we still want to take it apart, measure it ourselves, and say, no, I made this better.
It's the hot rodder's ego. We just cannot leave well enough alone. We inherently believe we can outsmart the factory engineers, no matter how good their robots are.
And as long as that spirit exists, I think blueprinting is safe. We will just find smaller and smaller things to measure.
I think you are exactly right.
Well, that brings us to the end of our time today. This deep dive was presented by Bluewater Auto Restoration.
A huge thank you to them for keeping the lights on here and supporting the gearhead community.
Absolutely. Don't forget to visit BluewaterAutoRestoration.com. Go check out the site. There is a lot of great info there. And remember, you can find our full archive of deep dives on Spotify, YouTube, Apple Podcasts, or SoundCloud.
Subscribe so you don't miss anything. We have some really cool deep dives planned for the rest of the year.
Join us next Saturday for Week 11. Until then, keep measuring, take your time in the garage, and we will see you next time.
Take care, everyone. Keep those engines running.